And you've almost made it. I'm your final obstacle before dinner. So, hi, I'm Fitz from Monash from Australia, and I work with Daniel and Ilya. So, many of you probably know Daniel. And I'm gonna talk about why do TDEs shine in optical and radio. So first of all, from many talks of these 2 days, we see we got too many observations of TDEs. We got them in X-rays, in opticals, in infrared, in radio, and also recently we got PEV neutrinos. And also possibly there could be some gamma rays, and that's too many, more than we can explain. So, yep, we got many problems here. And we also got many models. So for optical, we got there's shock powered model, there's reprocessing powered model, and you've heard enough, so I just skip this. And for radio, gamma ray, and neutrinos, we thought they could come from the interaction between TD outflows and circumnuclear material, which would then, due to the amplified magnetic fields, form synchrotron emission, which are observed in radio. And also there could be some hadronic reaction that creates neutrinos and gamma rays. But I've got a question, how does so many things fit together? And we got so many simulations, but they are just on different separate parts of the TDEs, and how does those fit together? So we choose to run some large simulation of a full TDE. And for that, we start with an initial star and run all through the TDE process until 1 year post-disruption. And for that, we use the GISP H-code phantom, so that's fully generativistic. And instead of polytrope star that's usually used for this kind of large simulation, we use a real initial star that's evolved from a 1 solar mass, 1 solar radii pre-main sequence star with the MESA code until the current solar age. And we didn't include any spin, so it's just a 10 to the 6 solar mass crucial black holes. And we run it with, we run some 10 million particle simulations, but they're too expensive and they're still in process. So I only present the 1 million ones here. And since it's expensive, we choose to do eccentric TDEs because they have shorter time scales. And also deep encounter, beta 5 is really deep, and that's also for the sake of time. So, yeah. Got it into the black hole. So that's a video, and I've got many movies here, so relax. That's a video of the column density of our simulation. And here we got a bright spot, which is the initial star, and also some black thing there. And as we can see, we got, at the first paracenter passage, we got a normal disruption. And on the second, we got stop collision. And then we got a normal disk formation. So everyone agrees with this, and everyone knows about this. But one thing that's usually ignored in past simulations is that we all look at those high density part. So that column density range is pretty high. But if we zoom out, and so that's zoom out by 20 times, and look at a bigger density range, so into the lower density gas, and we see there's much more things going on. So that's the outflow we, I guess predicted, because I didn't really see many outflows from the simulations. And we see that's lots of outflows. And that's what proposed to form those reprocessing layers. And also, if we zoom out more, we can see that things goes to more than thousands of AU after 1 year. Yeah, I have to speed up this video a lot, so we can show like a year in 20 seconds. But that's just density. That's not what we will see in observation. So in observations, we have opacity. So, and for it to be the processing layer, it needs to be optically thick. So which we assume only the electron scattering opacity here, and we try to do some ray tracing and rendering stuff, so we can get a sense how it actually looks. And I'm going to show a video in a sec. And what we see is like the photosphere would expand initially, and then as it expands, the outer layer will cool down, so the photosphere, it contracts, and which makes the whole photosphere at roughly a constant radius. So, outflow. So here, that's the expansion phase. So that's about 8 days for a planet-centric and beta-5 TDE, so pretty fast. And then as it goes, we got some sorts of breakout here at 50 days, but after that, it kind of settled down and turns into some quasi-spherical thing. So as time goes, even the things keeps outflowing, like the photosphere radius remain roughly constant. And then we try to, of course, we can't just look at the videos, we need to do some analysis, otherwise we can't get a paper published. So, yeah, I forgot that. So that's the photosphere, and we're just rotating it to see it from different directions, and we see it's roughly quasi-spherical. And the temperature is around 10 to the 4 kelvins, so which is a bit lower than the observed one, but that could be due to our like opacity assumptions. And then, yeah, there's one more thing. So that's the profile, like the profile of the gas envelope or the processing layer at 100 days post-disruptions. And we see, like in the very center, from the accretion, like the gas is kind of quite hot, so more than 10 to the 5.3, I don't know what that is, but more than 10 to the 5 Kelvin, so that will emit in the soft X-rays. So if somehow we can see through like the outer gas at this point, we could possibly see the soft X-rays. And what else? And also we got like in the middle part, it's relatively, I would say it's quite radio symmetric. So it's not like a disk anymore. In any way, it's like a sphere. So that's a bit contradictory to the past knowledge, but that's what we see. But even though it's radially symmetric, it's like rotating at a subcapillary way, and that's also somehow like the accretion disk. So it's pretty complicated in the middle part, but in the other part, we see it's not symmetric anymore, and it's just random gas from outflows, which could be the repressing layer. And it's also almost radial, like pure radially outflowing. Yeah, that's the key part. So we would like to do it with a proper radiative transfer code, but due to some problem with the scattering, our code doesn't work, so we did it in some cheated ways. We are assuming every particles are emitting as a black body at the local temperature, and assuming electrons only the electron scattering opacity, and we are tracing like from back to front according to the radiative transfer equations, and until like to the observer at infinity. And then like for each time frame, we will get a spectrum which we took the optical UV band and X-ray band and trying to fit black body to just those part of the full spectra. And as you can see, the optical spectra is the orange dotted line, and the X-ray part is the green dotted line. So the topmost one is with electron scattering opacity, and then since we are not really sure about what opacity should we use, we tried several different opacities. So that's electron scattering opacity, and we judged it by 10%, well, factor of 10 and the factor of 100. And also we did some like combined electron scattering opacity with wavelength frequency dependent free. I think we did hydrogen free opacity. That's it. And like as we decrease the opacity, we are looking deeper and deeper into the gas envelope. So we are looking at hotter and hotter parts, so we get more and more X-rays. And the free opacity actually there's I don't know how to explain it, but it gives X-rays in some weird ways. So just give a sense of which layer are we looking at with each opacity. So that's rendered with spectrum scattering opacity, and that's 10% and 1%, so jump by a factor of 10, 100. And as you can see, we're looking at very different layer of the reprocessing layer. So it's a big question, what's the true opacity we should use? Yeah, and by doing like those ray tracing and black body fitting to all time of our simulations, we get some sort of like curves, and we can compare them to the observations, which are those dot at the end. And I would say it's relatively good agreement between the two, given like we don't have too many assumptions to begin with. And the luminosity we got is roughly 3 times 10 to the 43 ergs per second, and the radius is like expand like how big at the start and remain at about 200 AU for the rest. And the temperature is like always about 10 to the 4 Kelvin. And they all stay roughly constant over the year. So why don't like any of those decay is a question. It could be like we didn't include any cooling in here. We did everything as adiabatic, or like we didn't include radiation pressure, which should be significant here. But that's open question, and we need to do like future simulations with those things to make some conclusions. And here might explain a little bit. So the only thing, so the blue curve is the one with beta 1, but it's like a low resolution simulation, only 100,000 particles, so we didn't really focus on that too much. And for the rest, it's beta 5, and the orange is 10,000 particles, and the green ones are the 1 million particles, what you just saw. We also, let's go. Hopefully that works. Yeah. And what I'm up to. So green ones are those like the previous ones with different opacities, and we also try to get a light curve from different viewing angles, where are those like just a bunch of mass here, and so that means it's almost identical in different viewing angles, so you can't really tell any difference. Yeah, I guess so the conclusion from here is we want to say like the penetration factor is not too important, and the viewing angle is not too important, and also the resolution doesn't change the light curve too much. But the only difference is the opacity. So if you have a look at the green lines, they shift a lot. So by looking at different layer of the reprocessing layer, we're getting really different light curves, and that's the only thing we find to change light curves. Yeah, and I've still got radio in my title, so we try to do radio. Excuse me. So what we do for radio is we first set up a spherical symmetric silicon nuclear material shell around the black hole from like 10 to the 15 centimeter to 6 times 10 to 17 centimeter, which is an arbitrary choice. And the parallel density profile is R to the minus 1.7. That's what I got from one of the observations, just by random choice. And the density, so to decide the inner density, I choose to set like the total mass of the shell to be around 0.1 solar mass, so it'll be comparable to the mass in the outflow. So there will be like significant collisions between them. And also it's set to be cold and stationary. And a problem about the resolution is like in the radius, there's many really few particles, so there's some like physical shocks happening at the start of the simulations. Yeah. And to simulate the shocks between the outflow and the circumnuclear material shell, we try to inject, so we got the previous simulations and we got the outflows, so we keep tracing the outflows through times, and we got some random choice of radius here, so which is something 10 to the 14 centimeters. And once the outflow, like the outflow from previous TD simulation passes this radius, we will inject that into this new simulations, and they will interact with this circumnuclear shell. And since our current simulation has no magnetic fields, we cannot like produce some synthetic synchrotron emission without some arbitrary assumption on the magnetic field. So we choose just to focus on the shock part instead of trying to produce those synthetic emissions. Yeah, that's the last video. I think so. So we get an outflow. It collides with the circumnuclear shell and forms some shocks. So the rendering here is the entropy. So higher the entropy, stronger the shock. And we are looking at from 3 different orientations and see like we got some quasi-spherical or quasi-ellipsoidal outflows, and it's like forming shocks in every directions. And if I do the, no, let's skip that. So when we looked at in temperature, so at the shock part, the temperature would be around only 100 to, well, few hundreds of Kelvin. So that's pretty cool, and they are not high enough to provide enough ionization to produce like enough free electrons to form those synchrotron emissions. So we are not too sure what's the source of ionizations here. So what's the source of those free electrons here? So not open question yet. Yeah, if we look at the profile, we see there's like the shock part is quite distinct. You can see the entropy increase a lot. And from the continuous shock between the outflow and the shell, like the region is like keep heating up to at about 10,000 Kelvin. Even like other parts keep cooling due to expansion. And also, I'm not sure if you can see or not, the outflow decelerate a little bit, but not too significant. So it could be like because the mass in circumnuclear is not high enough, or we need some other things to do that. And yeah, we did the same thing as the optical Leica. So we got radius, velocity, energy, and some magnetic fields from observations. So what they infer from observations. And we try to extract similar properties from our simulations and compare with the observations. And as we can see, the radius and the velocity agree with the observations quite good, especially for the dash dot one, where we got really low density in the circumnuclear shell. With I don't know why, but we suddenly got that high velocity, and it matches one of the observation pretty good. So just leave it there. The problem for the energy is like the total energy we got in those shock region has pretty small range, but from observations it's like pretty large range, so more than 6, 7 orders of magnitude. And yeah, and in this plot we don't only have the previous simulation with beta 5, we also have the beta 1 simulations. We also have other polytropics TDEs, so they should have quite different energies, but somehow they are not. So, and since we don't have magnetic fields, we're trying to estimate some magnetic fields. So in observation, it's usually assumed energy contained in the magnetic fields is like 2% of the total available energy. And when we do that, so that's what the magnetic fields we got. So it's slightly lower than most of the simulations. So that could mean we actually more energy are contained in the magnetic fields, or I don't know. And we see like the penetration factor and the eccentricity only make some quantitative changes, so like increase. So moving from eccentric to parabolic, we decrease the total energy by 1 order of magnitude, and so I think that's the only thing it changes. So the main thing to make changes is the mass in the circumnuclear material, or the density of it. So most significant is the dashed dotted line. So we got large radius and large velocity, and also much lower magnetic field here. So why is that? Is that really physical? Not sure. It's still work in progress. Yeah. So what's more, we want realistic TDEs. And so as I mentioned previously, we don't have radiation pressure and we don't have magnetic fields, so which is all the things I'm going to implement it. And so for the magnetic fields, well, I'm not too good with GMHD, so if anyone knows and wants to help, please help me. And yeah, I'll leave at the summary slide, and that's QR code to the optical paper we got. Thanks.
Any questions? So I actually had a question. So in your third to last slide, the one where you're showing all the properties as functions of yeah. So the E of 0.95 disruptions. So the star in that case is actually fairly tightly bound to the black hole on its original orbit.
Yeah, it is.
So I would think, so do you see, I guess I'm trying to make the inference from the plots, but do you, I would think there'd be a pretty big difference between 0.95 and 1, just in terms of the amount of energy that you can get into the outflow.
That's what we expected. Actually, you can't really tell the difference here without knowing which one's which, so that's a surprise. And we don't really know why, like, it gives similar things. Mm-hmm. Yeah, we don't really have an answer for that.
Yeah, thank you. So I have a question about the spectrum calculations. It was written on the slide that the particles emit as black body. Do all particles participate in the emission, or only a fraction of them?
Sorry, can you say that again?
Do all particles participate in creating the spectrum, or only a fraction of them?
So all the particles. So we are basically going from back to front and stacking like black body upon black body, and like it's also decaying with distance according to the optical depth. But we are stacking like every particles on top of each other. And finally we got that spectrum.
I would expect that only the particles at some photosphere would participate in the spectrum. Maybe
so when we do this, we don't really care about the photosphere. So we just go from the back and we start with like probably just one particle with one black body. And we got another particle at different temperatures, so another black body. And so the previous one was like faded a little bit due to the traveling distance, and we add a new black body on top of that. And until like at the end, we got that spectrum.
Yes, I have two quick questions. The first one is, you didn't say much about the differences of your calculation and the ones by Clement several years ago with the same parameters, but with different stellar structures. So maybe if you can comment a little bit on the differences. And the second question is very quick. What's the mass ratio between the outflow and the disk? So how much mass goes in the outflow and how much stays in the disk?
I think for the first one, I don't think Clement did some simulation with the real star.
No, not with the real star, exactly.
Yeah,
that's the question. So he had the same parameters in orbital parameters, but a polytropic star rather than a real star. So what's the difference?
Yeah, so one point of this one is trying to see if the real star will make any difference. And it doesn't for the beta 5, but for like lower beta, we got another beta 1, and it shows quite differently. So that's for beta 1, and we see that even like, so usually at beta 1 and it's eccentric, we will think it's like fully disrupt on the first go, but it's not. It takes like 5 orbits to get fully disrupted. So I think that's the most significant difference we see to have with a different stellar profile. And what else?
The other question was how much mass is in the outflow and how much mass is in the disk?
Yeah, so for the beta 5, the outflow mass is about 0.6 solar mass.
So most of it is in the outflow and very little is in the disk?
Yeah.
So 0.4 is in the disk and 0.6 is in the outflow?
Yeah, so even as like fully bound to star with, like 60%, like more than 60% is outflowing, only the other 40% is accreted.
Okay.
Nice simulations. So you have eccentricity of 0.95, and so the peak time scale is probably like a week or less, right? For like when you're dumping most of the mass on the black hole or near the black hole. Is that right? Like, I was just assuming that for this it would be probably.
Sorry, can you say that again?
So one of the differences with doing an eccentric case is you're kind of when it's noticeably eccentric like that is you're shortening your like energy distribution a lot, and so you're kind of dumping all of the material on a lot quicker to the black hole, right?
Yeah.
do you think that that has something to do with the sort of the fact that like when you do compare with observations, your light curve is kind of flatter? Is it kind of, I guess I would naively think then that the dominant time scale afterwards would be, and I guess maybe this isn't the right simulation for it, but would be like a viscous time scale or some sort of circularization time scale, since you're not mass limited. You've kind of dumped all your mass on the black hole immediately. Is that an accurate representation? I don't know.
Yeah, I'll have a similar response to like Eric's question. So we would think it would like show quite different light curves, but from what we got is like kind of similar to the parabolic ones.
Okay, interesting.
So I'm not sure how do we distinguish from like parabolic in the real observations. Not sure if you realize we got so many like fluctuations here, but we are not sure like how many of those fluctuations are actually physical or just like due to our cheating like ray tracing thing. So, but I would bet like some of the fluctuations here are like physical for eccentric TDEs, because for like the other, we've got some parabolic simulations and they don't show such fluctuating things. So we could possibly distinct like some eccentric TDEs in the future when we recognize which fluctuation is like true for eccentric.
Thanks.
Okay, let's thank our speaker again and all the speakers in the session.